All right, so now we are going to transition a tiny bit. And so far, our entire class has been getting values from some distribution, right? So we're saying if you can get random uniform, you can do all sorts of stuff and now get values from the normal distribution, values from a beta distribution, values from any other distribution that you can think of. As long as you've got the PDF, you can do something, either a transformation or rejection sampling or whatever it might be. You can now sample values from any random variable or any random distribution, okay? And what we want to do now is we want to take that ability to draw random samples and use that to evaluate integrals or evaluate, effectively, okay? And so now the topic that we are going to cover is called Monte Carlo integration. Monte Carlo integration. And this is all about evaluating integral, I guess the Monte Carlo way. Generally we would use it integrals by using the computer's ability to draw random samples. Okay, and the applications of this are things like calculating the mean, because the mean is equal to the evaluation of an integral, right? So application is basically if you want to calculate, so finding the mean. So let's say you wanted to find out what is the mean of some function. Okay, so this is a situation where x comes from some distribution. Maybe we'll call this some distribution f of x, okay? And we want to know what is the integral, or what's the expected value of the function applied to this random variable, okay? So, so the way we write this is the expectation over f of h of x is going to be equal to the integral over the random variable x of h of x times f of x dx, okay? So this is equal to the expected value of the function h of x over some random variable x. Okay, and all right, so before we get there, let's just say we want to evaluate some kind of integral first, okay? And so this is how we would go about doing it the Monte Carlo way, okay? So let's say we have some function h of x. Okay, and we want to find the integral, which will be, we will say I is the value of the integral, and it will be in a kind of a defined space from a to b of h of x dx, okay? Now, this thing could be the form of this could be difficult. It doesn't matter. Even if it's easy, this is still going to work, okay? And so what we can do is we can kind of work a little bit backwards, and we can say, all right, the average value of h over this space, okay, on the interval, AB is going to be 1 over b minus a times I, okay? Or 1 over b minus a times the integral from a to b of h of x dx. Okay, and this being a this being a constant, okay, so we can rearrange terms. And we would get the integral from a to b of h of x times 1 over b minus a dx, okay? And this here, 1 over b minus a, this is equal to the PDF of, if we call this f of x being 1 over b minus a, that is the PDF of what? Uniform from a to b, right? And so this whole thing just becomes equal to the expectation of h of x, where x comes from uniform a to b. All right, is that good with everybody? So we're just going to say the average, or the expectation of h of x is just going to be the evaluation of this, and so the integral, thus the integral, the value of the integral, can be equal to b minus a times the expectation of h of x. Okay, sorry, I don't know why I'm loosely switching between square and curved braces, but they're equivalent. Okay. All right, so to do this the Monte Carlo way, so we might call this simple Monte Carlo integration. And this will be the kind of the uniform case. Right? We will say we are going to generate a series of random values drawn from the uniform distribution. Okay, I'm going to close the online poll soon, so if you haven't responded to the online poll, make sure you do so right now, and the attendance choice is A. Okay, so if you trickled in here a little bit late, respond to the online poll, option A. All right, and so to generate a series of random values drawn from the uniform, we will write it like this. We'll say x1, x2, x3, dot, 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 all the way up to x super n are drawn IID from the uniform on the interval a to b. Okay, and then we plug these values into the function. Okay, so compute h of x of 1. Okay, so compute the function for each x. So that would be hx1, hx2, dot, 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 all the way up to hxn, okay? And then we get an estimate the expected value of h of x with the simple Monte Carlo estimator. All right, so that's going to be h bar sub n this is equal to 1 over n times the sum of h of x super I from I equals 1 to n. Okay, so basically just take the mean of all of these values, right? Just the sample mean of all of your Monte Carlo values. Is that okay? And that's going to be your simple Monte Carlo estimator. And if we plug that in here, then our estimate of I will be, I'll call this I hat. So n is going to be equal to b minus a times this quantity here, okay? The times the Monte Carlo estimator, h bar sub n. So this h bar sub n is an estimate of the expected value of h sub x, or h of x. Is that good? I'll let you guys get that copied down. I'm going to go ahead and close our pull down. All right. Does this process kind of make sense? All we're doing, yes.
Does it only work if the x is from a distribution that only ranges from a to b?
Yes. So this will only work on a kind of a closed interval. Okay. You can't have an open-ended interval right now. We'll cover that in a moment. So yes. So we have a closed interval from a to b, and we want to evaluate some kind of the h of x, the integral on that interval. And so the way we do that is we just keep drawing values of x, and then we calculate the function for each of those values drawn, and then we take the average of all of those things. And that's kind of like the average value across that interval. And then if we want to get the value of the actual interval, then we just multiply it by the width of the interval. All right, so let's just explore some properties of kind of our Monte Carlo estimator. Okay, so All right, so the expected value. Okay, so what is the expected value of this thing? Okay, well this will be the expected, by its definition, will be the expected value of 1 over n times the sum of h of x super I from I equals 1 to n. All right, so this is going to be 1 over n times from I equals 1 to n of the expected value of h of x super I. Well, x just comes from basically, well, each realization of x is from the random variable x, right? So each realization of x, x super I, is from the random variable x. So that's just going to be, so I mean, this is kind of a trivial step here. Okay, and then we got 1 over n times the sum from I equals 1 to n, and this will just become the expected value of h of x. Okay, so the expected value of our Monte Carlo estimator is the expected value of the function that we want. It's just that, you know, this depends on, well, for it to be accurate, you know, we need lots of values. Okay, and of course, any one individually drawn thing may not necessarily be that close. Okay. But that's what we have there. So that's the expected value. Let's take a look at the variance. Okay, so the variance of our estimator, h bar sub n, is going to be the variance of our Monte Carlo estimator, 1 over n times the sum from I equals 1 to n of h of x super I. Okay, and again, each realization of x super I is from the random variable x. So, so I'm going to go ahead and just pull this 1 over n out. When you pull a 1 over n out of the variance, you get 1 over n squared, right? Anytime you pull a constant out of the variance, so we're going to get 1 over n squared times the variance from I equals 1 to n. I need to somehow make better distinctions between my n's and h's. 1 over n squared, and then h of, can I just skip, oops, I need the variance term. Can I skip over the step that went from this with x super I to just h of x, because again, each realization of x of I is from the random variable x. Okay, all right, and so this becomes 1 over n squared. The sum from I to n, this is all going to be, the variance of this is going to be constant. So we've got the variance of h of x, and so now we get 1 over n times the variance. So the variance of our estimator is going to be 1 over n times the variance of the function. Okay, and so if we plug that in to our estimates of I, okay, so using our results, the expected value of h bar of n is equal to the expected value of h of x, and the variance of h bar n is equal to 1 over n times the variance of h of x. So these are our results. Then we can talk about I hat is equal to the value b minus a times h bar of n. Okay, and so we can say, all right, so this is our estimate of the integral. From a to b of h of x dx. Okay, so the expected value of I hat will be the expected value of b minus a times h bar of n. This becomes the b minus a times the expected value of h bar n, and that just becomes b minus a times the expected value of h of x, which is equal to what I is, right? So the expected value of I hat is I, that's desired. So this is, so what does this mean? So I hat is an unbiased estimator of I. It's always a good thing. Well, in general, it's a good thing. Okay, and then the variance of I hat will equal the variance of b minus a times h bar sub n. This becomes b minus a quantity squared times the variance of h bar n. Here I get b minus a squared over n times the variance of h of x. Okay, and so far so good? Great. Okay, and furthermore, by the central limit theorem, we can use this. Okay, so the law of large numbers basically states that h of n will converges almost surely. It's like a technical term, but just basically converges almost surely to the expected value of h of x. Okay, that's what we said. And then, so it's not just the expected value of h of it, our estimator is this, but the value itself, as n gets larger, will converge to this thing, right? So let me back up. Okay, so what does the law of large numbers state? Okay, so one thing, the law of large numbers basically states that the sample mean will, if you have an estimator that's a sample mean, it will converge to its expected value, okay? Okay, and so we know that the expected value of our estimator h sub n is equal to the expected value of h of x, and so we also get that the estimator itself converges to h of x, okay? So the estimator h of n itself will converge to the expected value of h of x as n goes to infinity. Okay, and so by the central limit theorem, all right, so what does the central limit theorem tell us? Yeah, we're going to have that this thing, if we so the realized value of h bar n minus the true mean divided by 1 over n times the variance of h of x, this converges or will come from standard normal distribution. Okay. All right, so let's say, so this is the example from our textbook. So our textbook is very, it's very terse, okay? You get, you read page 65, and basically everything we covered is just on one page here. Okay, but it's everything we've covered. It's all just condensed down. So, but it's a good reference there. Okay, let's say we've got some function. Okay, so this is the example, textbook example. On page 65. H of x is this thing. Cosine 50x plus sine 20x quantity squared. Okay, so h of x is equal to the quantity cosine times 50x plus sine of 20x quantity squared. All right, and we want to estimate, let's estimate, what are we going to try to estimate? Let's estimate this over the interval 0 to 1. Okay, so this becomes 0 to 1 cos 50x plus sine 20x quantity squared dx. Okay, and over that interval 0, 0, 1, our f of x is equal to just 1, right? So if x comes from uniform 0, 1, then f of x is just equal to 1, okay? And so this, we get the expected value of this thing. So this is equivalent to having 0, 1 h of x times f of x dx. I don't actually have to change anything, and this will become the expected value of f of h of x. Okay, and so all I'm going to do is to estimate. We're going to just generate many x values from uniform 0, 1, plug in x into h of x, and then average the hxi to get h bar n, which in our case is what we want. Okay, so let's try that out on our machine. Here, well, let's see what let's see if Wolfram Alpha can do this for us, and we'll see if it can give us a precise answer. Okay, so we'll say the integral from 0 to 1 of, what do we have? Cosine 50x plus sine 20x squared. All right, so it gives us this picture, and it tells me it's approximately equal to 0.96520. Okay, and I mean, we might have been able to do this analytically if we felt like it, but I certainly don't feel like it, because integration is like my weakest ability for math. Well, there's lots of things I'm bad at, but integration would be one of them. All right. Okay, let's try this out. You guys also saw homework 2 poster, right? Okay. It's not too bad, right? Okay, all right. Nobody started it. Huh?
I'll let you know later.
You'll let me know later. All right, okay. All right, so what we're going to do is we're going to just get some random uniform values. Let's set n equal to what? 10 to the 6, like a million? Okay. Okay, and our unif already goes from 0 to 1. All right, and then our h is going to be a function of x, and it's going to return back quantity cosine of 50 times x plus sine of 20 times x quantity squared. Okay. All right, let's just plot this for fun. All right, so we're going to plot, I guess, so I'll create a sequence. S will be sequence from 0 to 1 by equals 0.001. We probably don't need that much precision here. All right, so we'll go from S and h of s to type equals L. Let's go ahead and plot this out. All right. So that looks just like what Wolfram Alpha said it would look like. So that's that. Okay. And we want to evaluate this. So let me just kind of. So the idea here is we're going to try to get like the average of this thing, okay? And then by getting the average and then multiplying it by its width, that's going to be equal to the value of the integral, okay? And so how do we get the average of this thing? Let's just, if I just, here, let's do this. Y is equal to this, and then I'll print y, and then we'll also print h of y, okay? And I'll just, so if I plug in 0.7, that takes me to, I don't know, something around here, and it gives me 0.02. And then if I just run it again, it'll give me something like this, and here, I'm going to just do a for loop for I in 1 through 100. Let's and we'll do points y and h of y. That doesn't illustrate what I want to do here. Here, we'll go back. Okay. I'll just run this manually a little bit in the beginning. Okay, so here I pick a random y, 0.024, I plot it, and I say what's it equal to, and I plot it, and I get this value. So far, run h. Okay, so far if I ask what is the mean of the values that I've seen so far, I've only seen one value and it's 0.642, okay? Here I'm going to just sample another random value, and that goes down there. I don't know if you guys can see this, maybe I'll say color equals red and PCH equals 19, and we'll say CX equals 0.5, okay. So I put a dot right there, and then I'll kind of concatenate that to what I have. And so the mean of the two values I've seen, which so far have been like 0.64 and something around 0.6, if I take the mean of that, the mean is 0.35, okay? And if I run this again, I plot another point right here, okay? And now what's the mean of this, this, and this? The mean of all three of those values is 0.56. Okay, and then I take another random point, it ends up right here, and I say what's the mean of these four values, and basically I just keep repeating this, and I'm going to update my mean accordingly. Does that kind of make sense? So as I'm going along, I'm just picking random points along the curve, and as we go, we're just updating our mean, and eventually, this is too much, but so here I did like 1,000,000, and basically I'm going to have 1,000,000 different values, and I'm going to just ask what's the mean of all of this stuff. Okay, so I'm going to just ask what's the mean of h of my h of x. Okay, and the mean of all of those things, I get 0.9666969. Okay, this is the mean of 1,000,000 random points drawn along this curve, and I'm not going to plot them all because it's just going to look like the entire curve. You know, what's the mean of all those values? I get 0.96696, which is close. It's not exactly what Wolfram alpha spits out, but it's a pretty good estimate. Okay, and if I drew another random million points, and I say what's the mean of those, I get something a little bit different, 0.96468. Okay, and so if I average those two, I would get the average of across 2 million points and things like that. Okay, it's not hard right now for a computer to generate a bunch of random uniforms, and so I mean this is it. This is the entire code. You don't even need this to get your Monte Carlo estimate. Okay. Monte Carlo estimate of h of x, and then if we want to get the Monte Carlo estimate of the integral itself, we would take this. I should say of the expected value of this. Okay, we would take this value and multiply it by our interval width b minus a, which in our case is 1, so it doesn't change. Okay, but that's what we have. All right, are there any questions on this? Okay, I guess I've run out of time. I was going to cover the case where we have an open interval, but I guess we'll do that on Wednesday, or we can go from like 0 to infinity or something like that. But this is where we're headed. We're going to start off with kind of by being able to randomly draw samples along some interval and then evaluating the function. And there we can get estimates of the integral. Okay. All right. We'll end here for today. On Wednesday we'll do the open case, and then we might start important sampling as well. Okay. Just review. I guess review your notes and then see if you can understand just a short version that's printed in your textbook in Chapter 3 on classical Monte Carlo integration. So start there, and then we'll go forward.